So I'm gonna talk today about a thing called the principle of mathematical induction, PMI. But throughout this discussion, I want you to have a particular analogy in mind. Usually I would do this in class with dominoes, but I'm home and I don't have any dominoes at my house, so I've got books lined up. But think about one of those things where people set up dominoes and you topple them with my books. What do you need to know to be sure that sort of all of these books are going to fall over? Well, there's two things. Somebody's got to knock into the first book to start the process, but also they've got to be close enough together that when one of them falls, the next one's going to fall. So those are the two things. The first one's got to drop, and each one along the line has got to make the next one drop. Right? So, well, that time it worked, but let me take a second and reset this thing up. Maybe I'll put this in fast motion when we're reviewing this. But suppose the gap between some of these was a little wider. Like something like this, for instance. Now, if I topple things, it only goes so far, and then it stops. You see the point that we need to know that for every n, the nth one falling is going to make the n plus first one fall. So let's do some more formal stuff. So that's the analogy. PMI, or Principle of Mathematical Induction, says if you want to prove something is true for all n in the natural numbers, some statement P of n, that it's the same thing using a sort of a two-step procedure. It's the same thing as if you actually have the and of two different statements. What are those two different statements? The first one is that the smallest natural, that kind of doesn't matter whether you call it number one. Oh man, this isn't going to be framed right, is it? No, it's okay. So it's the same thing whether you think of this as the 0th or the 1st, or sometimes we can change this set as long as it's a sequence of statements, an infinite sequence. But let's think about the natural number starting with 0. So our first book that drops would be 0. The thing is true at 0 when n is replaced with 0. And the second thing is that not that P of n is true, but rather that P of n forces P of n plus 1 to be true. Because I'm anxious about that issue of using the same variable for two different things, I usually say this in terms of some new variable. So for all k in the naturals, if P of k is true, we want it to be true also that the next guy, P of k plus 1, is true. Right, so this is the first domino, or the first book drops, and this is if the kth one drops, it'll make the k plus first one drop, so that they're all close enough together. We don't have that gap somewhere along the way. Yeah, so let's run some examples of proving things using mathematical induction. We had a couple of formulas for sums of sequences in the last section. So one of them was that the sum of just the integers, I, going from 0 to n, that is n times n plus 1 over 2. Right? So I'm just saying that's the right formula, but let's now give evidence for it. Let's actually support it. So I'm going to prove this. You'll see that this is a different statement for each value of n. So this thing here is our p of n, and when I say a thing like this, I guess it's implicit that I mean it's true all the time, that all n's work. If I want to be more explicit about that, I can say for all n in the naturals, that sum is true. That sum is equal to that formula. All right, so we're going to prove this using the principle of mathematical induction. So I always like to do this kind of thing with my proofs, is give a little parenthetical hint to whoever's reading it what method I'm using. Unless it's a direct proof, then you can just go. But all right, proof by PMI. So there are names for these two statements we've talked about. The first one that P of 0 is true is called the base case. Some people actually just say basis. I like the phrasing base case, which is that we want to show that the thing is true when n is 0. Again, that's just parenthetical. So what does the sum look like when n is 0? The sum from I equals 0 to 0 of I, that's got a single term in it, and it's 0, right? Okay. The other thing is, what does this formula look like? N times n plus 1 over 2, evaluated at 0. I'm kind of out of room here, but let me try to squeeze it. Make that 2 really tiny, and then we can do it. N equals, evaluated at n equals 0, that's 0 times 0 plus 1 over 2. Yeah, that's 0 in the top, so that's equal to 0. So the sum is equal to the formula and the base case. That means the first domino is dropped. What about the other phase of this? This is the part where the real work is. So how does that real work go? Get these books out of the way. Well, that, by the way, the name for that second phase is called the inductive step. And again, I'll put a little parenthetical thing in there to let us know what's happening in the inductive step. This is where you're trying to say that if the kth one is true, it'll imply the kth plus first one is true. One more parenthesis. Okay, so we're proving an if-then in this case, which is philosophically feels a little bit strange. Because how do you prove an if-then, right? You prove the if-then by saying, well, the if part is true, and then you try to deduce the then part. So we're going to assume that P of k is true. And here's where this is philosophically weird, but is actually okay. Remember the boilerplate sentence we had when we were proving a UCS? Assume that P of k is true for some particular but arbitrarily chosen k. This thing isn't universal right now. So I'm not assuming the thing I'm trying to conclude, which is that it's always true that P of k is true. I'm saying, assume we've got a fixed k somewhere down the line, and I can assume that's true. That's an important distinction. So assume that P of k is true, and what you want to do is show that P of k plus 1 is true. It's often the case that we'll stick in little advice to to the reader in proofs. So there's an abbreviation that people use, which is WTS. That just stands for want to show. We want to show what? Well, we want to show that P of k plus 1 is true. Can I just write T for true? That's what we're after. All right, so since P of k is true, what did the kth version of this sentence say? It says if you take the sum that starts at 0 and goes to k of I, it'll actually be equal to k times k plus 1 over 2. So, in other words, take the sentence we're trying to prove and just substitute k's where the n's were. That's what we get to assume. And again, we want to show that P of k plus 1 is true. All right, so how can we do that? Well, what would you do to the sum that goes from 0 to k in order to convert it to the sum that goes from 0 to k plus 1? You need that last term, the k plus first term. So let's do that. I'm going to add that term. Of course, I want to keep the balance, so I'm going to add that thing to both sides. Adding k plus 1 to both sides gives, what does it do? Well, by design, it's going to make this side go to, well, actually, first I'll just write it as if we just didn't know what we were doing, but really this is going to go from 0 to k plus 1 now. So I'll do that work in 2 steps. I equals 0 to k on this sum. But that k plus 1 right there is going to really turn this. You'll see that in a second. What about the other piece? Well, we just have a k plus 1 added to that fraction. All right, so I've got to move to the top of the board. Maybe I'll only scrub half of this, so we'll see how far we need to go. Like I said, that stuff can be re-expressed as a single thing. You've got a sum now where the index goes one step farther. Combining these first k, well actually it's first k plus 1 because it starts at 0, with that would be really the k plus 2th term. But anyway, combining those two things, get a single sum that goes one farther. And can we combine these two things too? Let's just find a common denominator. It's, this one doesn't have a 2 in the bottom, so let's make that happen. 2 times k plus 1 over 2 plus, the other thing did have the 2 over it, so that doesn't have to be changed. So, great. We're hoping that this looks like the formula when the n's have been replaced by k plus 1s. And it actually does. Just let's notice that there's a k plus 1 in each part of the numerator there, so you can factor that out. And then what remains is a 2 and a k. So let's write it as k plus 2. So maybe just to make it 100% clear that that's really the k plus first version of the formula, think of it as k plus 1 times k plus 1 plus 1 over 2. So the basis was true, the base case was true, and the inductive step, the part that says if one book falls, the next one will fall, is true as well. Here's a summation sentence. Since the base case is true, and the inductive step has been proved, it follows by PMI that the result is true. So then you can write QED or whatever you use as your end of proof sentence or marker. I'm gonna do a second example of this with another one of those formulas that we looked at on Wednesday. So I erased the board and wrote up the result we're going to prove. This isn't quite the way it was written on Wednesday's lecture, but it's the same thing. This is a sum from 0 to n of the cubes. So we're talking about adding up the cubes of the natural numbers up to some given point. The formula here is, what I had before was n times n plus 1 over 2 squared, and I've just carried out the squaring. So you square the 2 parts in the numerator, you square the 2 that was downstairs. That's just if you want to, we can think of this as the square of n times n plus 1 over 2. I'm just writing that, and I'm going to immediately erase it because it's just there as a hint to you that that's the same formula we did previously. All right, so the proof of this, we'll again use mathematical induction. And the base case is trivial because the sum is 0 when n is 0, and there's 0 cubed is 0, and there'd be a single term when n is 0, and this has got n squared in it in the numerator, so that's zeros. But if we want to kind of be careful, we should write out both of those things. So how does it work? When n equals 0, the sum from k equals 0 to n of k cubed, don't want to change variables in midstream, equals 0, and the formula there, n squared times n plus 1 squared over 4 is also equal to 0. Right. Make sure, by the way, when you're doing base cases that you do like I've done here. Figure out what the sum is, figure out what the formula is separately. Don't just write down that the sum is equal to the thing, because that's what you're trying to show. So that would be a begging the question kind of moment. All right, so that's our base case. The inductive step in this one. Well, in the inductive step, we're going to assume the formula is actually true we're going to assume that it's true when n is k. We're going to assume that k is a particular integer, natural number, and that formula holds if you stick k in where all the n's are. Well, you know what? I can kind of shortcut this on the board here. I'm going to use the fact that, oh, darn it. No, I've got a little bit of an issue now. I was trying to use k as my variable in the induction proof, but I was using k here as the index. Dang, no, I really wasn't. Look what I did previously. There's an error in here. I used k as the index there, but then I wrote I cubed. So we'll have to go back in time to fix that on the thing. I can't do that, but that really should have been, sorry, really should have been I equals 0 to n of I cubed. Let's see if I can now write the first line of the inductive step here. It's going to be assume that, I'm just going to change all the n's to k's. assume that that is true for some particular but arbitrarily chosen value of k. I don't need to keep writing out that particular and arbitrary stuff though. Okay, assume that that sum is equal to that formula for some k in n. What is it we want to show? We want to show that it's true at the next layer up, at the k plus first version. So what will we add to this sum to turn it into one that goes from 0 to k plus 1? Well, we're going to need to add the cube of k plus 1 to both sides. This time I'm not going to do it in 2 steps. The sum now goes from I equals 0 to k plus 1 of I cubed. But the thing on the right-hand side is a little tougher. That will have our k plus 1 cubed that we added to both sides, plus the formula that was there previously. Okay, so can we combine these things together? Sure, but we also need to keep in mind what our goal is. We're hoping that that looks like k plus 1 squared times k plus 2 squared over 4. I'm gonna write in green what I hope this is equal to. I hope that I'm gonna get k plus 1 squared times k plus 2 squared over 4. That's what I'm hoping. I hope that that thing is equal to this thing. That may help us to think about our strategies in doing the algebra to make that happen. So how would you do this? You need to have a common denominator. So I'm going to just go ahead and introduce that right now. Sorry, 4 is pretty sad. All right. And then we'll combine them using that common denominator of 4 and see what we get. All right, so everything will be over 4. Notice that there is 4 copies of k plus 1 cubed on that side and k squared copies of k plus 1. Well, let's pull out the things that we know we're after. You know, notice how we wanted to get a k plus 1 squared on both sides? We can do that. So write it as 4 with a k plus 1 squared factored out. What's left in all the other terms? There's 4 times k plus 1. And then there's a k plus 1, there's a k squared. We factored that out, so it would be times 4 times 1 more copy of k plus 1 from the thing on the left, which had k plus 1 cubed. And then we took so k squared, there. And it's all over 4. Right. What am I hoping that this part in parentheses is equal to? I'm hoping that it's k plus 2 squared. So a good trick to do in these scenarios is just to assert that the thing you hope is true is indeed true. Because it just looks like you were really good at algebra. But k squared plus 4k plus 4 is exactly k plus 2 squared. So that's correct. Even though you might argue that I've skipped a few steps. You're allowed to skip algebraic steps in a proof. We assume the algebraic stuff is something that everybody understands. All right, so that is actually the form we were after, although if you really want to get explicit, you can write it as k plus 1 squared times k plus 1 plus 1 squared all over 4. And that means that you've finished with the inductive step, and we previously did the base case. So conclusion is therefore by PMI, the formula is correct. There's a pretty terrible joke that I'm going to have to tell you at this phase, because the next proof we're going to work on is the sum of a geometric series. So the joke is an infinite number of mathematicians walk into a bar, and the first one goes up to the bartender and says, "I'd like a pint of beer." The second guy comes up to him and says, "I'd like exactly half of what my friend had." Then the bartender says, "You guys are all idiots," and he pours 2 pints. So why is that funny? Because what it says is this statement about numbers. If you add up the number 1 plus a half of that, and assuming the pattern continues, the next one is a half of the half, so a quarter, plus a half of that, which would be an eighth. And if you do that forever, that's equal to 2. Yeah, you may or may not believe me at this point, but we're gonna actually get down to showing that that's true. So what we're gonna do first, though, is prove this kind of a result for a finite case. How do we do that? Well, what does this sum look like? It looks like a sum of, let's use I for the variable, I starting at 0 and really going to infinity, but I want to stop at some particular spot, n. This particular sum starts with the 0th term is 1/2 to the 0 power, and then there's 1/2 to the 1 power, and 1/2 to the 2 power, and so on. So these numbers are all powers of a particular value, 1/2. Let's go ahead and write that, 1/2 to the I. Right. So how can we figure out what a thing like that is equal to? I believe that it's easier to think your way through this if you write out the expanded form. So this will look like 1 plus a half plus dot dot dot. What's the last term going to be? That's when you have 1/2 to the n power. And let's call this something. Let's call it S. S for sum. S equals that. Well, there's a cool little trick you can do, which is multiply S by 1/2 again, the same number that we were seeing in there. So 1/2 of S is equal to, well, what's it look like? It starts with a 1/2, and basically I'm going to take each one of these things and multiply them by a half. So I'll have a half plus a quarter plus dot, dot, dot. What will the last thing in that be? I'll have 1 more a half multiplied by this half time to the n power, so it'll be a half to the n plus 1. I feel like those should be in parentheses so that we aren't confused. Yeah. So compare these two things and think about what you get if you in them. You should notice that almost all the terms, actually including this one, are in here. The 1/2 up to the last term, all of those terms are in here. They're successive powers of 1/2. The way these two things are different is the second one has an extra term on the end that's a half to the n plus 1 power, and the first one has a an extra 1 in it, which is really neat. There's all this cancellation between them if we subtract. So, which way do I want to do it? I think I'm going to take a half of s and subtract s. That'll be a half to the n plus 1 minus 1. Right. Well, so far so good, except that, well, you know what? You can solve this for s. Think about this algebraic. That's just some number on the right-hand side. And there's an s in both parts of that. We can factor it out. This is s times a half minus 1 equals this formula we've produced on the right. 1/2 to the n plus 1 minus 1. So what I'm going to do is divide by that. So s is equal to a big power of a half minus 1 divided by, a half minus 1 is just negative a half, right? So actually, yeah, a big power of a half is going to be a small number, and when we subtract 1, that's going to be something negative. But then we're dividing by something negative. I think the two minuses are going to cancel out, and we'll get something nice. So let me give you an example of using that formula. If I added up from I 0 to 10 of the powers of a half, I should get, let's see, 1/2 to the 11 minus 1 over negative a half. Divided by negative a half, that's like multiplying by negative 2, and I can negate a thing by just turning the order around. This is equal to 2 times 1 minus a half to the 11. Whoops, I put the 11 in the wrong place. 1/2 to the 11 on the inside. Because I was trying to get to the punchline about my joke. You see that this is 2 times something that looks like 1 minus something that's practically 0. And when you let n go to infinity, you actually do get 0. So that's 1 minus a half to the infinity would be like 1 minus nothing. And so we get 2, just like in the joke. You can do this whole deal in general. So I did this for a particular value, the 1/2, but there's a general result. If you have a number r, let's see, I think we just want to avoid r being 0. And if we are hoping to do infinite sums, we want to keep r less than 1, but I can write the following. The sum I 0 to n of r to the I, well, it looks just like this result that I got. Well, let's do it this way. This thing that I got, just replace the 1/2s with r's. So it looks like r to the n plus 1 minus 1 over r minus 1. Which is pretty interesting. You can use that to do a lot of work with sums. This thing that I've just written there is called the formula for the sum of a geometric series. I've never been completely clear on why people call them geometric, but there are things that look like you're adding up successive powers of some fixed number r. The formula we just had for the sum of a geometric series was this. S equals r to the n plus 1 minus 1 over r minus 1. There is an extension of this that I should point out. If you have, well, let me give you an example first. Suppose we have the following sequence: 3, 6, 12, 24, 48, and so on. Now, you can recognize this as a geometric series by doing kind of analogous thing to we did when we made the difference table, except we'll divide rather than subtract. So we'll take 6 divided by 3, and then 12 divided by 6. You see those common ratios that you get are always 2's. And when you get that kind of phenomenon where look at the common ratio of terms, it's always 2's, you do have a geometric series, but this is not one that starts with 2 to the 0, then 2 to the 1. It starts with a 3. So the formula for this particular series is that a sub n is equal to 3 times 2 raised to the n power. So that's a geometric series, and it's sort of the most general form. You'll have a number out front, and then a common ratio raised to a power. So here's your general geometric series. It's a sub n equals some initial amount, I don't know, let's call it k, times a ratio between terms raised to the n power. So what do you get for the sum of that more generic form of geometric series? It's just the same formula here, but with a k up front, right? Because you can distribute k across the entire sum. Or maybe I put it the other way, you can factor k out of the entire sum. You see, this expression, well, that series, when you do its sum, that is the, I'm really squeezing it in at the bottom here, but sum of a sub n looks like, well, it'll start with a k, and then the next term will be k plus, times r, and then after that it's k times r squared, etc. I don't know, I didn't put limits on that sum, so let's say it starts at n equals 0, and it goes to n equals, I guess, m, use a different letter. So this sum would go all the way up to k times r to the m. So what is this sum equal to? Just by factoring out all those k's and then using the formula we just had, it's equal to k times r to the n plus 1 minus 1 over r minus 1. That's pretty easy. But this has a couple of great little applications that I want to show you. I think one of my favorite applications of that sum of a geometric series is this one. Think about what the number 0.99999, you know, where the 9s go on forever, is equal to. Most people think that this number is not the same as 1, and that's not true. This number is exactly equal to 1. There is no difference between 1 and 0.9s going forever. It feels wrong. It feels like the 9s should somehow be slightly smaller than 1 is. But if it's smaller, how much smaller? You can't ever name a number, no matter how tiny, that is the difference between these two things. So that's one way to think about it. But the other way to think about it is this number, the 9s repeating, is a geometric series, the generalized sort. See, this looks like 9 in the 1/10th place, plus 9 in the 100th place, plus 9 in the 1000th place, and so on. So you can factor a 9/10 out of every single one of these things, and you get 9/10 times, I I guess I should have put a question mark up there at the saying 0.9s forever is equal to 1, because that's what I'm trying to prove. This 0.9 is actually equal, is actually equal to this expansion. We're taking the 9/10 out, so we'll have 1 there, and 9/10, that'll be 1/10 left over. 9/10 out of that, that's 1/100th left over. You see this is a geometric sequence in here with, well, they actually call it a geometric series once you're adding up the bits of that. And what is the common ratio? 1/10 divided by 1, or 1/100th divided by 1/10. They're always the same, it's 1/10. So the K out front is 9/10, and the common ratio, the R, is 1/10. I don't know why I wrote one of them with a horizontal slash and the other with a diagonal slash. I'm just going to make them the same. Right? So this sum is actually calculable with the formula that we've been doing. The only thing that's weird, or that's, well, slightly weird here, is the sum isn't starting somewhere and then ending somewhere else. It just continues to roll. It goes forever. So what do you think you get when you add 1 plus 1/10 plus 1/100th plus 1,000th plus etc. going off forever? You still get the same result. One way to think of it is the 0.999 repeating is equal to, let's see, our K is 9/10. Well, we had that fraction that had R to the, well, I guess this would sort of be the infinity power of R minus 1 over R minus 1. That ordinarily, putting an infinity power on something would bother me, but think about what this means. If I multiply a number like 1/10 times itself a lot of times, it gets closer and closer to 0. And when you do it infinitely many times, this thing literally becomes 0. So what we've got here can be actually well understood as 9/10 times -1 over, whoa, what's R minus 1 going to be? The R was 1/10 minus 1 from 1/10, you get -9/10. So in the end, what I've got here is that the 9's repeating is equal to 9/10 times -1 in the numerator and -9/10 in the denominator. The 9/10 cancel, the minuses cancel. What are we getting? 1. So if that's not compelling to you, the other way to think about how come 0.999s when the 9's run forever is literally equal to 1 is this. If two numbers are actually different, then there should be a number in between them. I challenge you to name what that number would be. Because if it's larger than the 9's running forever, in some decimal place way out there, it's going to have a digit that's higher than 9. But there aren't any. Right? 9 is the biggest number the biggest digit you can have in a number. All right, so that will be that for this section on induction. The challenge, I think, for you guys is to prove the formula I've been using on a couple of these things. The formula for the sum of a geometric series, either the infinite sort or the kind that's not infinite, the kind that goes from 1 to a fixed endpoint, 0 to a fixed endpoint. Prove that and use mathematical induction to do it. It's a good challenge and it's not terribly hard, so I think it's something that's doable. All right, and I will see you Friday.